Okay, guys, thanks again for joining us. So, today we will be talking about how to achieve more with less in lens array. With me are our distributor in Africa, Mr. William, and my colleague Marco Meseric from 3D Survey. So, Marco will be our moderator for the presentation. During this presentation, if you have any questions, please just write them into the chat. So we will then, after 30 minutes or so, we will go through and we will answer those questions. And some questions my colleague might answer right away. So now I would like to give the word to our colleague William, who will say about a few words and make some short introduction.
All right, welcome guys to the 3D Survey and Some Survey Instruments webinar. We trust you are just as excited as us to jump right into it. Before we start, we just want to say thank you for taking the time to enjoy this webinar with us. And please feel free, as Vida said, to post all your questions at the bottom section. And if we missed a question, please send us an email afterwards and we will be sure to answer it. And if at this end of this webinar, you don't feel comfortable to take on a drone survey, please let us know as well. And we will assist with training modules and live webinar or live training as far as possible. We're just really here to serve you. And yeah, so just before I hand over to Vid, please make sure to stick around to the end as we've got a big surprise for you. Yes, all right. And then we all know that having to do surveys in the field sometimes can require us to go back into the field because we missed a few points or missed some data, and that's why drone mapping is such an amazing field. So I think in this webinar, you'll get enough information to see why this could save you a lot of time and a lot of money and extremely amount of efforts. And this will definitely teach you to work smarter, not harder. And that's what it's about at the end. Thank you. I'll now give you over to Vid. Thank you so much.
Thank you, William. Okay, nice again to meet you all. So I'd just like to make a quick introduction about ourselves. So we are a surveying company from Slovenia. We started developing this software in 2011, so almost 10 years ago. And by now, we sell this in over 35 countries worldwide. And we have around 2,000 licenses of this software sold. So a lot of people are already using this technology now. So now let's just go straight to the presentation and see what it is about. So what we are selling and promoting is a new surveying tool. Now one person in the field can do the work that many people did before. So just one person with a drone and maybe some sort of a GPS instrument can now measure terrains up to 10 hectares in size in just a few hours. So the drones they offer very good benefits for lens array because they now allow us to do stuff that only state institutions were able to do before with big planes and very expensive equipment. Now the drones on the market, they became so widely popular and so available, and it makes perfect sense to use them for lens array because they allow us to do more with less. And we are all like that. We all want to achieve more with less. So now let's go ahead and let's talk a little bit about today's program. So first, we will make some short introduction to photogrammetry and 3D survey. We will talk about the drones that are available for purchase, what are their benefits, which ones make the most sense to buy. We'll also do some theoretical facts about drone technology, about photogrammetry and 3D survey, how to map with images, how to do 3D modeling, and in the end, we will have some real case presentations. So we will go through a project together in 3D survey, so from importing images to processing them, and then hopefully we will have time for a few additional case studies to just check what everything that's possible. And in the end, of course, there will be questions and answers and conclusion. So as we said before, after maybe some 30 minutes, we will have a short pause. We will give you a short poll to answer some questions. And after that, we will, during each of these short pauses, we will also answer any questions that might come up in the chat section of this webinar. Okay. Now let's have a quick look at how this technology actually works. So 3D survey ecosystem, it consists of software for piloting the drone and software for processing the data. So as a land surveyors, what we do now, we just come out onto the field, we start up the machinery, go into the application for planning flight, we select an area of interest that we want to fly over. We can set some flight parameters like flying height and overlap. After we are done, we just press upload the mission. We press a button and the drone will take off. So in 15 minutes time, it can cover an area of 500 by 500 meters. So that's pretty good. Or it can map a distance of road of more than 1.5 kilometers. After the flight is done, we get a lot of images. These we transfer to our PC where we process them and we get some final results. The first result type is 3D point cloud. So this is a cloud of points, usually a few 100 million. It makes very good representation of natural environment. Out of the point clouds, we can create some 3D models, so watertight models, which can be used to extract contour lines from or calculate some volumes. So volume calculation is especially simple. All we have to do is select an area of interest and press calculate volumes. Also profile calculation, so that has never been easier. All we have to do is select where we want to have these vertical cross sections and press calculate. So no more walking on dangerous cliffs. And then last but not least, there is also a free viewer available. So here we create very accurate 3D models that some users might not, that your clients might not be able to open. And to empower them to use this 3D data, there is also a free viewer available with which you can just share these results so that the users can enter them and maybe just make some simple measurements. So for anything more complicated, of course, this is not included. Like volume calculations, you need to have 3D survey for. We don't want to have your clients calculating volumes without you. Okay, let's have a look at some bullet points of why to use the drones in land survey. So they are proving to be a very effective method of getting spatial data, which is what we land surveyors do. They are also an independent method. You know, I started working in land survey as a student some 15 years ago. And very often when doing mapping, we would make some errors. So you mislabel some points when you map them with total station, or you incorrectly connect some some excavation site, and you can very quickly make a gross error. So with photogrammetry, what you do is you create a 3D model out of pictures. So you are a lot less prone to make any of these kind of errors, because what you get, here you get a 3D model, and in the end you'll just be checking what the accuracy of that model is. If you make a gross error, it will show up because the pictures won't fit together. Okay, but more about that later. So even though this technology seems very complicated, you know, we have flying cameras that you have to operate, it's actually very simple and easy to use. So, you know, even kids today are playing with the drones, and these professional drones are actually a lot easier to fly than the small toys. Okay, then there's also the speed. As we said, in 60 minutes, we can map areas of up to 500 by 500 meters. And those 60 minutes, out of those 60 minutes, 30 minutes we will spend to map, to measure 10 ground control points that we might need for this kind of area. And last but not least, this technology has quite an affordable price. So you will see later, but the total cost of everything you need will be less than an average cost of a total station. A lot of this is helped by the fact that the drones are now so popular, everyone is using them, and the best price performance drones will cost under $2,000. Okay, now let's talk a little bit about hardware. So what kind of hardware is available to use for drone photogrammetry? So we kind of divide the drones into three parts. So first section is industrially produced drones. So these are the ones that you can go out and purchase. Second section will be drones assembled from parts. So in the beginning, this one was the only one that was available. So around 2013, 2014, even we were creating this kind of drones. During that phase, we learned a lot of stuff about drone technology. We were buying parts from China, putting them together, testing them, and we really learned a lot. And the last section is fixed wings. So these are a little bit different. Again, usually they are like on a half industrial produced or half made from parts, you know. Okay, what are the benefits of each of these categories? So these drones, industrially produced drones, most of them are Chinese. They are easy to use, small, reliable, and they are actually the least expensive category. Their only downside is that they have a single payload option. So usually you cannot change camera, but that doesn't really matter if this camera is good enough for what we need. So in the end, these are proving to be the perfect surveying tool because they are reliable, safe, small, and inexpensive. On the other hand, drone assembled from parts, usually they will be a lot more expensive than industrially produced one. Their benefit is that you can put any kind of payload onto it. So very often they will have different camera options. They are good for some custom applications, but they tend to be a lot more complicated to use. And the worst part about them is that some parts can malfunction. So servicing this is something that you need to do on a regular basis. So most of the time, these are only used by people who make them themselves because they are the only ones who can fix all the problems that can arise. So they will be okay for some custom applications. If you make one yourself, 3D Survey will also work with this one. If not, rather go with one that is that you can buy in store. And about the last section, the fixed wings, so they are good because they can cover a lot larger areas. They have flying times of up to 3 hours. So that's what the producers are telling us. So, but you can maybe count on 2 hours of flight. They tend to be a lot more complicated to use. Some you need to throw into the air at a right angle for them to start. Others might have a catapult to launch them. The downside is that they don't have any oblique images and they tend to be quite expensive. So north of 30,000 euros. But they can be very good for mapping very large areas like new railroad project, very big open pit mine for for areas over 10 square kilometers. These are the best ways to do it. For anything smaller than that, I would go with the first option. So just a quick slide to let you know why the drones can fly on their own. So these things, they really came very far. So this is an actual photo of DJI Mavic mini drone. You can see that it can fit into the palm of your hand. But even this small device, it has so many systems working inside of it, like compass, barometer to get height. They usually have GPS, GLONASS, Beidou, all of these different satellite receivers. They have gyroscopes inside, which is one of the most important things that allow them to fly because it tells them how which way is up, which way is down. One of very useful stuff inside is most of them also have photo sensors. So if you try to crash them into the wall, they won't go. They will stop in front of the wall and start beeping. And some IR sensors so they can also see in dark. So let's talk a little bit more about cameras. So a few years ago, when we were starting for photogrammetry, people were using what we called metric cameras. And here we see an example of metric camera. This one is called UltraCam. It's produced by Microsoft. And these were the tools that were used to map the countries or do photogrammetry. So this kind of camera used to cost somewhere around $1.5 million. So not many companies were able to afford this kind of devices. What has happened in the last 10, 15 years, the algorithms that we use in photogrammetry became so much more advanced that we can now get better results that people got 15 years ago from these simple small cameras. So this is example of a drone camera. Its total weight is probably around 100 grams. And surprisingly, out of this one, you can now get better, more accurate results than you would get out of this monstrosity that weighs 100 kilos. Okay, when we talk about cameras, there is one important thing we have to talk about. And most people don't know about this one. But when it comes to cameras, there are two types of cameras. I think we have all seen this kind of an effect in videos. So wait, just a second. This is called rolling shutter effect. And what causes this? So some cameras, they make picture simultaneously. The whole picture is recorded at once. While on other cameras, they are called rolling shutter cameras. And picture is taken like that, line by line. So it turns out that when it comes to mapping, the most important thing to have is to have global shutter camera. So in order to get nice picture without distortion. Why is that? Because this distortion is hard to model. In order to model it, we need to calculate how fast the drone was moving, because the speed of the camera governs the effect of this distortion. So for most accurate results, we recommend you to always use drones or cameras with global shutter. So the problem is, a few years ago, most of the cameras on the market were only rolling shutter cameras. So okay, this rolling shutter effect, it will be eliminated computationally. But if this effect is not present to begin with, we will be a lot better off. So now let's talk about which drones have a global shutter camera and which ones have rolling shutter camera. So global shutter camera will be present on Dji Phantom 4 Pro, Phantom Rtk, Autel Evo, EB, and Dji Inspire drones. And if a camera says that it has a lift shutter, then it's most likely a global shutter camera. On the other hand, most of the cameras, the consumer cameras available, they have a rolling shutter camera. That's because just how the CMOS sensor that they use is built. So a lot of very expensive, very big cameras that you would think will produce very accurate results, because of this rolling shutter effect, they will actually be less useful. So now let's have a look at some drones that are available for purchase. First one on the list is an example of a fixed wing. This one is called EB. I think they are made in Switzerland. They are kind of okay for mapping big areas. Their most important downside is they are made of styrofoam, and when they land, they don't have any parachute. So when they land, you have to land it on the grass. It will just come down, land like that. The problem with that is after 10 to 15 landings, you will probably have to change the hull and the wings, and that can be pretty expensive in the end. Other than that, it's a good drone. It has a specially made global shutter camera, but the quality of it might not be as good as other cameras available. So when you zoom in onto the picture, you see that it has a little bit of effect inside. A second example is this one is kind of interesting. So this drone is called Wingtra, and this one is a hybrid between multicopter and fixed wing. So it takes off vertically, and then when it's airborne, it flies like a fixed wing. So it gets benefits out of both categories. The problem with this one might be the price, because it costs more than $30,000. So not the most cost-effective solution, but they have a very good camera options inside, and they have RTK GPS support. Another example of a good fixed wing is called Bremor. This one is slightly more expensive than EB. It costs around 40,000, but it is very well made out of carbon parts, and it has a parachute so that it can land safely. The downside on this one is it's very big. Just to launch it takes around 1 hour time, but it has, I think, the best flight time available of any drones. Okay, then there are drones assembled from parts. So this is example of the drone that we were building here at our office. So this is how it looks when it's put together. Before you fly, you just extend the arms. So it has 6 propellers to make it safer. The problem with this one is with the Chinese part, it's very hard to make sure that you won't have a problem with cameras not recording or something like that. I think we sold around 20 of these back in 2014, 2013. I think around 5 of these are still flying. We started making these because at some time there were not enough drones available, so we made this one and we sold it for around $8,000. The but only the parts you need to put this together will cost you around $3,000 or something like that, 3 to 4,000. Okay, now we are getting to the affordable and industrially produced drones. So this is now what actually most people are using today. This one is called Dji Phantom 4 Pro. So the price on this one will be less than $2,000. It is made of plastic, but it is very safe. Of more than 1,000 people I know that are using it, I know only of 2 crashes, and even those 2 were due to user error. When after doing survey, they were, flying around and taking some pictures in manual flight, and then they maybe flew too close to the tree that had no leaf on them, and it got tangled into the branches and fell down. But even those, they were pretty inexpensive to fix, so they just sent them back to DJI. DJI took out all the parts that they were able to use, and they sent them a refurbished drone for something around like $700. So for the half of the price. So that's a pretty good one. A second option on the list here is Dji Phantom Rtk. What's special about this one is that it has a special RTK antenna. So usually drones, they have regular GPS on board, and accuracy of that GPS will be around 5 to 10 meters. With an RTK option, you can actually get a centimeter grade position for each photo. So that can help with the accuracy. In the end, it will require you to set up less ground control points if you use one of these. And I think the price on this one will be around $6,000, something like that. But don't hold me for my word on this one. Another very interesting option from DJI for people who want to have something smaller is called DJI Mavic. This one, when it folds together, it will actually fit into your pocket. The downside on this one is that it doesn't have a global shutter camera. The drones that we spoke about earlier all have global shutter camera. This one only has a rolling shutter camera. So that makes it less suitable for land survey. Other than that, it's very good because it's smaller. It has the same performance as the bigger drones, all the added sensors, but the fact that it has a rolling shutter will mean that you will need to set up more ground control points if you want to use something like this. And the price on this one is the same as DJI Phantom. Okay, another option, so alternative to DJI would be also Parrot and Effie. So this one is actually kind of similar to Phantom. Most of people want to use this one if they plan to use it a lot close to the airport, because DJI products, they have geofencing inside, so the drones won't want to take off if you want to fly it less than a kilometer away from the airport. These ones, they are not so widely used, so they don't have any of those kind of limitations inside. It also has a rolling shutter camera, so with this one also you will probably need to set up a few more ground control points. One of example of a drone is also this one, Unique. So a few years ago they were very popular, a lot of people were considering them, but they turned out not so good. We just put them here just to warn you about it. So the problem on this one is that the flight time on it will be around 7 to 8 minutes compared to 25 minutes on other drones, which makes it quite less useful for land survey, because in 7 and 8 or 8 minutes you have to land more often, change more batteries. Also, the price on them, they cost more than DJI products, and they also turned out to be somewhat unreliable. I heard about quite a few crashes, so maybe not the best choice to make to buy one of these. And also the new kit on the block would be Autel Evo. So this is now a new company from United States. They seem very good from the specifications. They just started shipping Autel Evo 2. It will have a global shutter camera. There will be actually different camera options available. The price will be a little bit higher than DJI products, but for this one we have to wait and see. So some clients, they don't want to buy DJI products because they are Chinese. So if you don't want to buy Chinese products, I think this is the best solution. So for those people who want to have also quality at affordable price. So here in Europe and in United States, this will mostly be government institutions, because they have some security concerns, and I think this is the drone to use for those kind of applications. Okay, now we talked a little bit about the drones. Now we can just make a short break, and let's check a little bit the chat section. Also, my colleague will now turn up the poll for you to answer just a few quick questions. So Marco, please go ahead and start the poll, and I will just open the chat section to see what is going on there. I see that we have some questions. Okay, Caleb was asking us what's the difference between rolling shutter and global shutter. So the difference is rolling shutter, it takes image like that. It records the top line, second, third, fourth, fifth, and so on. And it will take around 30, 40, 50, 60 milliseconds to do that. So in 60 milliseconds, the drone might move a few 10 centimeters or something like that if it's flying at 6 meters per second. I see that the results of the poll are already, okay, sorry about that. So then in order to calculate the effect of that distortion, we have to calculate how fast the drone was going. And to do that accurately, we need to have more ground control points. So because of that, always go with global shutter if you have that option, because global shutter will record the image simultaneously. So no need to calculate how fast the drone was going when we use it for photogrammetry. Okay. Now let's check out the results of the poll. So I see that we have 2/3 of people coming from surveying and mapping industry. 10% in construction, 10% in agriculture, 5% in inspection, and 2.5% in mining and education each. That's very good. I see that the numbers, they are still changing a little bit. Until now, 60% of people have answered this survey. So the second question now here in the poll is, are you already using 3D data like point cloud, slider data, 3D survey maps in your workflow? So the numbers are coming in. By now, half of people have responded. Let's wait a few more, maybe a minute or so. Okay. And now the numbers are starting to stay at the same. So around 35% of you are already using 3D data in your workflow, and 65% are not using it yet. So okay, I think very good to have this webinar to let you know what all the options are available. And now the next question, are you already using drones for mapping projects? Okay, more than half of people have answered already. Well, that's very good. I would say almost surprising results. We are now more than 70%. 70%. We have over 70% responses, and 45% are saying yes, we are already using drones for mapping projects, and 55% are saying not yet. So very interesting to learn. Now the next question, if you are already using drones, what kind of results are you producing most of the time? So the results are coming in. So based on the previous 45%, okay. Okay. I think by now most of people who said that they are using drones have already answered. Almost half of you guys are using drones to produce orthophoto maps. So 45% use drones to produce orthophoto maps, 7% for volume calculations, 11% for profile lines, close to 20% for production of contour lines. So very good option, yeah, because the most effective way of getting contour lines. 11% for production of textures 3D models, and 7.5% for CAD drawings. If you ask me, I think using drones for CAD drawings, it can help speed up our process a lot. Okay, volume calculations also, but you have to have projects where you can do volume calculations. If you can, they will offer the best benefits, but we will see about that later. So, okay, now I would like to just continue with this presentation. So we talked a little bit about drones. Now let's talk about how we can use drones in land survey. So we'll just go quickly through this, not to waste too much time, what we can do with cadastre, how we can use them in construction, mining, an example of inspection, what we can do for environmental monitoring, agriculture, and emergency response. So first one is for cadastral maps. So this is actually what most of us land surveyors do. I mean, most of land surveyors, they work in cadastral projects. So here actually drones can be very useful because orthophoto map, you can extract some valuable information out of it. So you can, instead of measuring roads and edges of buildings and everything out in the field with TotaStation. You can also just create a 3D model and then extract these line works out of the 3D model. So that way we can speed up our work a little bit, and the added benefit will be when we will make a map, we will also have a nice picture to go along with it, and the picture is worth more than 1,000 words. So it will, it will make the maps more understandable also for people who are not architects or civil engineers who are used to working with this kind of data. So another very interesting application is used in construction. So in construction, it might cost around $10 to excavate 1 cubic meters of material. So then, it's important for the guys doing the excavation and for the guys who are paying to know exactly what the volume of the excavated material was. And very often, you will have two different surveyors, one working for the guy doing excavation, one working for the one who is paying. Both of them make measurement, and in the end, they have to come to the same result. So now, just to map this small area, just to measure it with the TotaStation or GPS, it will probably take you more than a day. With the drone, you can do that in 1 hour, and in the end, the result will be a lot more accurate, because with TotaStation, you can never take in all the small bumps and perfectly measure all the points that you need in order to calculate volume. So that's why this technology has such a big added value in construction. Similarly, also in open pit mining, quarrying, and stockpile management. But here the main thing is we are talking about even bigger areas. Here the walls of the excavations will very often be very steep. It can actually be very dangerous to walk here close to the edge and map this kind of stuff with TotaStation. So here, actually, if you ask me, there's no other technology than drone technology to use. Even laser scanning here would be impossible, because you would have to move around this area all the time, setting it up, and in the end, you just get nowhere. So another interesting application is, so drones also open up some new field for land surveyors. So it also allows us to do inspection of various built objects in order to do some defect mapping, because this is a very cost-effective method. Again, it will give us HD, so high definition visual control. We will be able to make side orthophotos of the objects that we are inspecting, and then nicely analyze stuff in the office. So here we have an example of highway support column. So these were a kind of projects that we were also doing some maybe 5 or 10 years ago. Before, the guys who are the government institution who is making sure that the roads are being safe, they had to buy a big ladder to come, and then to climb here and map all these defects. It cost them, I think, around 5,000 a day just to rent the ladder, and they needed it for a lot of days. Now with the drone, you just fly there, you take pictures, create a map out of those, and then they can map these defects in office and calculate when they need to go back and fix this support pillar, for example. Okay, another example, what we can do is for environmental monitoring. So this is example of landslide measurement. So when we have terrain that is changing, it can be very effective if we can just make some orthophotos out of it. And then we can just compare the orthophotos and see how the terrain is moving due to landslide. And then geologists, based on this information, they calculate how dangerous the landslide is, and if they need to do some safety measures like dig some wells add some support pillars, something like that. And this kind of data can give you some actionable results. Okay, last but not least on our list is the emergency response. So because drone survey is so fast, it's very useful for this kind of applications. So sometimes you'll have some rock falls. You will maybe need to know how many trucks you need to take away this material. Very often when we have this kind of projects, there will be some geologists. In order to plan the defensive measurements, they will need vertical cross sections to plan some defensive nets to stop the fall of rocks. With drones, we can get these results in very fast. So actually we can have the results done the same day. So this will allow us fast response. So now more and more police and fire departments are starting to use drones. Policemen also use them to map the traffic accidents. Firefighters use them to get a better sense of what's going on with fires, to see where the fire is still burning, where it's not, these kind of things. So it's proving to be a very useful technology. Okay, so this was a little bit about what we can use. Now let's talk a little bit about theory. We will now look at algorithms that allow us to get from photos to useful 3D results. So we will very quickly look at bundle adjustment, orientation or georeferencing. We look at dense reconstruction, so this is point cloud calculation. Then we will look at how we can create digital terrain model, what the difference is between digital terrain model and digital surface model. And in the end, we will also check orthophoto and what is classical orthophoto, what is true orthophoto, like that. And also, we will look at what's important to get accurate results. So we will look at some algorithms again, so RTK, GPS, and these kind of things. Okay, the first on the list is bundle adjustment. So bundle adjustment is the algorithm that we use to bundle the images together. So this one is kind of interesting one. So this is actually an algorithm that works similar to how our human eyes work. So if we have some images recorded from various angles of one object, and we don't need to have any information on the perspectives that the images were recorded from, just the images themselves, they will be enough to calculate the basic 3D shape of this subject, and they will also allow us to calculate where the images were recorded from. So now let's talk a little bit at how this is possible. So what we are doing, we are calculating where the images were recorded from, and we are already calculating also the basic shape of the terrain. So how this works, so the whole bundle adjustment algorithm, we can split it into 3 parts. So the first part is detection of feature points. So there are some algorithms that allow us to detect interesting points. So these points will be sometimes like a corner or like a blob or something. So this first algorithm will find this kind of interesting feature points. And for each of these feature points, it will calculate what it's called a descriptor. So it's like a fingerprint, it's a number that describes very well, that describes this point. Then the second step of bundle adjustment is feature point matching. So when we have feature points and descriptors, we just go, we take first point on the first image and we compare it to the first point on the second image, and we see how well they match. And we do this for all possible point-to-point combination, and we try all possible image combination. In the end, what we get are 2D matches between images. So we have image 1, image 2. If they will have a similar scale, then the matches will be like that. They will go in parallel. If they have different scales, they might go like that, or they can even be rotated. but always there will be a certain pattern to them, and that helps us distinguish the right matches from the wrong ones. Then the main part of bundle adjustment is calculating the 3D data out of these matches. So when we start, we don't have any information on how the images were recorded, one in the relation to the other. So it actually turns out if we have at least 5 matches between 2 images, we can calculate the solution, how the images were recorded one versus the other, just by making sure that all the rays intersect. So here it's actually some quite interesting math going on, but for this demonstration I will just skip that part. What's important to know is when we have matches, we can calculate how one image is recorded in relation to another, and it will also allow us to calculate the 3D positions of these feature points. So this is similar to, like in old days when we had total stations that were not yet total stations, but only allowed to measure angles. So you would place a theodolite on first point and measure vertical and horizontal angles to some detail points. Then you would move to another one and again measure those detail points. And in the end, you would triangulate those 3D points. Well, here we also must calculate some more information. That's why we need to measure more points from the same positions. What's important, that allows us to from these matches to calculate the bundle adjustment. So result of bundle adjustment will probably look like something like this. So if we have a grid of photographs, it will allow us to create what is called a sparse point cloud. So these are those feature points in 3D, and it will also allow us to calculate the accurate positions where we recorded photos from and what angle the camera had when the photos were recorded. So that's the first important part. So you will see later when we go to the software that it's completely automatic. You just press bundle adjustment, next, and it happens all automatically. Then there is the second part. We need to make the 3D data accurate. So at first, bundle adjustment, it may use some telemetry information from the drone, but usually, it will not be correctly placed or rotated. So then in the next step, it's important to make that data accurate. So the best way to do that is by using some ground control points. So we have an option to georeference with ground control points. So prior to flight, we will place some ground control points on our terrain and we will measure them with a total station or a GPS. And then in the next step, we find those ground control points in our photos and we use that information to make our results accurate. Another option is to georeference it with telemetry information. So we can do that if we have a RTK drone that has a centimeter grade accuracy of camera positions. And then in that case, even better option is to georeference with both GCP and telemetry. Because telemetry, you still have to know when drone is flying. For each measurement, it will have less than 1 second. So, it's like mapping with GPS and only taking one measurement for each point you measure, it might not be accurate enough. So even if you have RTK GPS, it's still best to georeference with both GCPs and telemetry. Okay, then the next step is point cloud calculation. So this algorithm is ideal for GPU because here what happens for each pixel on photos, let's say we have 2 photos here. So for this photo, what we do, we try to find the same point on second photo. So if we take this point here in the left view, we know that the point that represents this in 3D will lie somewhere on this line. So if we project this line onto right view, this might come up something like that. And we then just move here and we check, is this point similar to this one? Yes, kind of is. This one? No. This one? No. This one? No. We say, okay, if this one and this one is the same, this corresponds to this point. So because we have to do that for millions of pixels at a time, this is ideal for GPUs, because GPUs, they have 1,000, 2,000, 3,000 cores. That means that you can calculate for 1,000 pixels at a time, and in the end, if you have a GPU, it will allow you to get better results in less amount of time. Our result of point cloud calculation will look something like this. So here we have a nice point cloud of urban area. So this one is actually Netherlands, I think. So this was one flight with the drone. I think the length of this is maybe around 400 meters by 200 meters, so a small area. And the point cloud here, it has everything inside, all the trees, all the buildings, all the building boundaries, the fences, and this kind of stuff. So pretty interesting what the technology now enables. Because, you know, with Total Station, probably we would need a few days to map this kind of area. Okay, let's check out an example of point cloud. So at this point, I would like to talk a little bit more about the point cloud. So let's see a real example. So here I have example of a point cloud. So this one is actually not created in 3D Survey, but it's created in one of the most widely used softwares available. So when we are calculating point clouds, it's very important how we do it. That will govern how much of noise we get in our point cloud and how sharp the point cloud will end up looking. So the competitive softwares, they may get you something like that. On the other hand, 3D Survey has one of the best point clouds algorithms available. So you will see that the result is a lot sharper. Here we calculated 6 million points with the same settings. In competitive software, we only had 3 million points. So that's only half. And then, okay, if only this was available, probably this would look also pretty amazing. But if we want to map something, if we want to make some line work out of this, then it's very important that this data is as good as it can be. So that's why we also invested a lot of our time into getting this kind of data out of the pictures. So we worked very hard in order to make this sharp and with as little noise as possible. So just one more time for the comparison, competition versus us. A lot sharper, a lot more detailed. Here you can even see the people who were flying the drone. Okay, let's go back to the presentation. Okay. Now with point clouds, an important step of processing is also classification. So as land surveyors, very often we need to know what the shape of the terrain is if we want to extract contour lines, for example. So usually when we get the point cloud, the first step will be to do the classification of the point cloud. So in 3D Survey, this is very simple. It's semi-automatic procedure. All you do is select the wizard, press next, 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 and you end up only with ground points. So why we use ground points? We use them so that we can then later create a digital terrain model. So out of the ground points, we create a regular grid, And then out of this one, we will be able to extract contour lines and everything like that automatically. On the other hand, if we make a 3D model out of unclassified points, then what we get is a 3D surface model, or DSM. So this one also has buildings and trees and cars and everything like that present. So out of this one, you wouldn't want to calculate contour lines, but it can be useful to create orthophoto out of that one. So Orthophoto, so this is a Google Earth-like image. If you look at it, you will see all the important stuff that we want to know about will be present in this image. It can be very useful to quickly draw a map of our area of interest because everything is present. So here it will be very hard to make some gross error, like incorrectly draw where the building edge is, because we just see how it looks. And now, if orthophoto is calculated out of digital terrain model, in that case, what we will get is the classic orthophoto. So in that case, the building roofs will not be correctly positioned. On the other hand, if we calculate orthophoto out of DSM, then what we get is what we call true orthophoto. In that case, also the roofs of buildings and trees are exactly where they are. So both have their benefits and weaknesses, and we will check that later. Now let's quickly look at what kind of results we can get also from this data. So first one is contour lines. So once we have the digital terrain model, all we have to do is press calculate contour lines. We select the equidistance, press calculate again. It just takes a few seconds and already we have the result. So now this we can export into CAD to be used with our survey drawing. So there will be an export available, so pretty straightforward. Okay, let's go on. So next, one of the most interesting things is ability to create some line drawings. So it will take a good team of 2 surveyors, probably around 15 to 20 seconds to measure one point in the real world. So if we want to measure, I don't know, 100 points, 100, that's it will take, I don't know, between a half an hour or an hour at least. It will still depend a lot on the kind of the terrain we are measuring. So if we can, on the other hand, just draw these points in 3D instead, this will be a lot faster. So here you see it all. I have been speaking about this now for I don't know, about a minute, and we already measured here 20 points. So this technology, it can be around 10 times faster than measuring points in the field, and it will be just as accurate. We will check later what the accuracy of this data can be, and you will see that the accuracy that we can get this way will be around 2 to 4 centimeters. With 4 centimeters, something that you can be sure to get, but if you work well, if you make enough ground control points, actually what you can expect out of this is around 2 centimeter accuracy. So that's about the same as what you will get out of the GPS. And then instead of mapping everything out in the field, you can just make a 3D model and then map in your office. Okay, when it comes to vertical cross sections, again, when we have the 3D models, all we have to do is select where we want to have the cross sections and we can just draw them. So, compared to, walking like that down the line and measuring points all the time, again, a lot faster. And there's also an added benefit that after the survey is done, you can just select where you need vertical cross sections. So when I was still working as a student, as a regular land surveyor, very often it would happen. We would finish a project, and then a month later, someone would call us and say, "Hey, here we need to have some more vertical cross sections. Please go and make a few more." And then you would have to go there and make them at no additional cost. And it takes time, a lot of energy. Here, if you get that kind of request, you just create a new cross section where they request it, and that's it. Okay, then volume calculations. So with this technology, volume calculations have never been simpler. Here we have an example. We have two point clouds. So for the 2 point clouds, we can create 2 digital terrain models. Then in order to calculate the volume, basically all that we need to do is select our area of interest. So if we were doing this for real, we would do that very accurately. So here we're just doing that real quickly just to show how it works. So we can then see very well what the difference between the two surfaces will be. Then in order to get volume, you just press calculate volume. You just wait a few seconds in order to get the result, and already you will have the volume calculated. So pretty fast and effective technique. And after you do that, you can also get an automatic report on the volumes, just in combination with some vertical cross sections. You can have projects that would take a lot of time and energy to calculate. They will be very simple. Okay, so now also generate report, measurement report. Just select which volumes you want inside, which vertical cross sections, select the name for the file, and what you will get will be a Word document showing you where you calculated the volume, what the volume was, and where we have those vertical cross sections, and also the cross section view. Okay, so we've spent an hour talking. Let's just continue. Now I just want to talk to you a little bit more about what's important in order to get the accurate results. So first one, the most important thing is photo quality. So I have here some examples of not so perfect photos. So it's important for photo to be sharp, and this one is not. This one is not because the exposure time on it is wrong. So exposure time, that means how long the shutter is open. If it's open for too long, the drone is moving while it's taking pictures, and in that case, you will get this kind of effect. So you will get things that are supposed to be points will become lines. And if you have this kind of effect, you know that the exposure time is wrong. Okay, so this is now an extreme case. But for lens survey work, exposure time should generally be lower than 1/100th of a second. So on the camera you have a setting. It will be 1/10th, 1/30th, 1/100th, 1/200th, 1/300th, and so on. So in summertime, this is usually not a problem. It can be a problem in wintertime when days are shorter and darker. So at that time, you have to pay attention to those exposure times in order to get sharp images. On the other hand, it's also important, if you have photos can be overexposed. So this is example of overexposed photos, and you see that here you have areas that are completely white. So in this kind of completely white area, there will be no feature points, image matching won't work, and what we will get here is just an empty spot in our point cloud. So it's also important, to have the correct exposure settings. Then, okay, also another important thing is it's important to use the correct camera. So I'm not sure which camera this is from, but some cheaper drones, they might not have very good cameras, and you get a lot of different effects into it. You see the picture here, it's not very sharp, and here where there is some bush, there is some effect there, and if you will try image matching on this, it might work a little bit, but all of these artifacts in photos, they will affect the results, and they might not be as accurate as they should be. So then you ask what the good photo looks like. Okay, so the good photo will look very sharp, and you can tell that it's sharp if you zoom into the photo. If you zoom in so that you can see the separate pixels, if the separate pixels, you can distinguish one pixel from another like that, then you have a good sharp photo. If photo is unsharp, this will look like, smooth. You won't be able to tell this is pixel 1, this is pixel 2. They will have very similar color. Here they have different colors, the separate pixels. Okay. Now also let's talk about resolution of our data. So resolution is the most important. It's one of the important stuff, but we don't want too much of it because then our results will be too big. So with this, I would like to tell you our thoughts on the perfect resolution for this kind of aerial data. So we tell this to everyone. So even when we started, we tested various different flying heights. So here I have an example of photo recorded with DJI Phantom 4 Pro at 40 meters, at 80 meters, and at 120 meters. So we think that flying the drone at 80 meters high will give you the best ratio between the photo size, the result size, and the quality of the data. So with Phantom 4 Pro, it's like that. If you fly it at 40 meters, you will get resolution of the images at around 1 centimeters. At 80 meters, around 2 centimeters, and 120 meters, the resolution will be 3 centimeters. If you fly at 160 meters, resolution is 4 centimeters. It's linear. So if we look at the quality of the results, I think flying lower than 80 meters, it does not make sense, because even here we can see everything that's important for us to see. So you can see here in this courtyard, you can see separate stones in this floor. You can see very well what the manhole cover looks like. Here, if you fly at 1 meter, you don't get that much added value. On the other hand, if you fly higher at 120 meters, it's already hard to distinguish all the small cracks. So if you ask me, 2 centimeters, that's about that. So that will be 1 pixel in the resulting orthophoto. That will get you the best result. Also, if you do it like that, orthophoto size will be only a quarter of this one. So here you might get orthophoto 100,000 by 100,000 pixels. It will be very big. If you will put it into AutoCAD, it will crash. If you fly the same area at 80 meters, it will be only 50,000 by 50,000. So that's 4 times less pixels, 4 times less memory. A lot more people will be able to open that kind of orthophoto. While this one, the resolution will be even lower. So the orthophoto resolution will be lower, but then the quality will not be good enough anymore. So that's why for your projects, my recommendation is fly at 80 meters high. Okay, to get the good results, what will be also important will be the correct perspectives. So for most of our projects, we will just use the basic grid flight configuration. It's just important to use the correct overlap, usually between 70 and 80%. Sometimes we set it so that the overlap will be 80% and side lap will be 70%. So with that kind of flight, if we place 10 ground control points on our area of interest, we can expect horizontal accuracy to be between 1 and 2 pixels, and also vertical accuracy will have a similar accuracy. We can check on project later. What's important, doing it like that, we will get accuracy that will be better than 4 centimeters. So, okay, here we say 1 to 2, 1 to 3. If you do everything perfect, the accuracy will be better than 4 centimeters for sure. So when we plan the mission, the recommendation is like that. If this is our area of interest, we draw the area so that the flying path will be just slightly over our area of interest. That will allow us to get very bigger area of interest, but the best accuracy will be in this central part of our model. So this part on the edge, you know, it has less side lap, so this might not be as accurate as this one here on the inside. So for longitudinal objects like roads, railways, something like that, it will be similar. Here it's important to always use a minimum of 3 lines. So sometimes people fly and they just make, you know, one line like that. In that case, you don't have any side lap, you only have overlap, and that's no good. So always you need to have a minimum of 3 lines. If you use 4, start on this point, fly like that, the drone will come back to you. So it will not take much longer than 3 lines. For very big areas where we map 2 kilometer sections at once, we usually stand here in the middle and then we just fly the 3 lines and it's enough. And with Phantom, you can map up to 2 kilometers. Okay, maybe for start only map kilometer or kilometer and a half. The problem when you do that big distances is the terrain can, you know, go up, down. You have to take that into account when you plan this mission. And then, okay, let's also talk about setting up ground control points. So as we said earlier, the ground control points are the most important part that allow us to get to the good results. So, and it's important to spread them out nicely. So we will spread them out both in 2D, so horizontally and vertically. So ideally we will, especially if we are working with stockpiles, we will put one on the highest point, one on the lowest point, and, you know, also cover the XY extremities of our areas. And when placing the ground control points, you know, we just try to place them so that the distance between neighboring ones will be between 50 and 100 meters. Okay, if we have very big area, then we can also place them out so that the distance between neighboring ones will be 200 meters, something like that. If we are mapping roads, then the advice is similar. Again, we put them at a distance between 50 and 100 meters, but in this case, we just put them on both sides of our linear objects. So 2 here, 2 here, 2 here, 2 here. It's good to place them together because then when we will be picking them up, we will work faster if they are not that far apart. And before we already mentioned the terrain, so our recommendation is when you do mapping, always start the drone from the highest point on the terrain. So this is good for 2 reasons. First one is safety. If you start from the highest point, you're less likely to crash in some tree or something like that. And another important thing to consider is also overlap. So if you start at some lowest point of the terrain, you set up the mission at 80 meters high so that the overlap will be 80 meters. So here the terrain and the house might be 45 meters higher. So here the drone will be only, let's say, 35 meters over this house. That means the overlap will be less than 50%. And, you know, that's already a critical value. So that means that images are not overlapping over the whole area. And here this part may probably not even calculate anymore. So you can get holes in your model. So always start from the highest altitude, and even over the objects you will get good overlap. And so just a general word of advice. Okay. So now we did the theoretical introduction. Now let's look in practice how processing a dataset works. So let me open here a new project, a new 3D survey window, and I have here a nice small project that I can process here in real time. So this is 3D survey. So here to start processing, we can just click images, load images, or we can just click here on new project. So now I'll just move to this presentation folder. I have here a nice small data set of 34 images. So after selecting the images, the software asks us if we want to import the telemetry information. So most of the drones, they write telemetry information into EXIF data. Other ones will write it in a separate file. Here we can set our coordinate system and our GeoHit model like that, import. So what we have now, here we have where we flew the drone, and we also have information in 3D where we recorded the images from. Now, as we said before, so what we have here are images and very approximate positions where the images were recorded from. Okay, before the flight, we placed around 10 ground control points out on the ground, and we measured them with the GPS. Now let's start the processing. As we said, first step is bundle adjustment. So this one is completely automatic. We just press OK and we start processing. So bundle adjustment is a pretty fast algorithm. For these 34 images, it will take less than 2 minutes. So if we had 1000 images, 600, 700, 800 images, it would take maybe an hour, maybe 2 hours. Okay, again, it will also depend a lot on the speed of the computer, but you know, it goes up a little bit exponentially. So if you have twice as big project, it might take 3 times as long to calculate than the smaller one. So now the feature detection is already done for the images, and those features were matched between those different images. And now the software is actually already calculating from where the images were recorded. So, okay, so this laptop is pretty good one, so that's why here it will finish in now, just about now. And this is the result of bundle adjustment that we get. We get already the approximate shape of the terrain, and we get more accurate positions where we recorded these images from. Now comes the second step, that will be georeferencing or orientation. So here we will now add the ground control point information. So ground control points, I have them here in this GCP file. So the file with ground control points, it just looks like this. We have a point name, easting, northing, and elevation. Okay, let's close this. Import. Now let's go to the next step. So now here we just need to find the approximate positions of these ground control points. So in our software, it has one of the most user-friendly methods of doing that. So here is already our first ground control point. So, and these red dots, they are the feature points, you know, that were detected automatically. That's why when we mark one ground control point on one image, we also know its position on all the neighboring images already. And because of that, we only need to mark 3 ground control points. So here is already the second one. So ideally you will not mark 3 that are exactly in the line. So usually this won't happen if you select sort of okay. So here is the third ground control point. After we mark the third one, the software will automatically recognize which ground control points we have already marked. Now what we can do is we can just check. So it's important that all the ground control points are inside of this circle. So if we want to move this one, we can also improve the position of this one a little bit. Like that. Maybe let's check it also on the other side. So 12. And then, you know, I see this one. This one was causing us a little bit of problems. We'll just remove that one. 13 we will just clear. Okay, now everything fits together. So one click was not accurate enough, but now we have what we need. All the ground control points are inside of these circles, everything fits together. Then we have here this detect GCP targets checkbox. So then the software will go and inside of this circle it will try to detect the center of black dot. And here we already have results. So now, for example, ground control point number 2, it's visible here on image DJI 899, 900, 901, 911, and so on. So here what we do is we just go quickly through it. We could add this measurement manually, but it has a little too much glare, so we will just disable this one. We just check how the automatic detection went. It went perfect. We could select or deselect points like that. For example, we can remove one like this if we don't want it, but it's okay, so we'll just leave it inside. Then we just press next, and then this information gets added to our 3D model. And then what we get here are ground control point errors. So that's now the difference between where we have measured our ground control points and where are with GPS and where these ground control points are in our 3D model. So here we see that we get around 2 centimeters. That will be the maximum offset. So a good rule of thumb for this data is to say the end accuracy of the results will be about similar as the worst error that you get in here. So that's a good rule of thumb. So for this one, probably we would get around 2 centimeter accuracy. So if one point here would have 4 centimeters or more error, we would just go back and check how that point was defined. Now let's just press finish. And now our model here is georeferenced with these points. Okay, now let's continue on. So we have here a point cloud. The next step will now be point cloud calculation. So this part is actually the one that takes the longest, but in our software you will get the best result available. So on my machine it takes around 1 hour to process 100 images. So here we have 34 images that might take around 20 minutes. Too long for us, so I will just load in a pre-calculated point cloud that I already have here, just in order not to waste any time. And this is the result we would get after some 20 minutes of processing for this small data set. Okay, but this is an area of 100 by 100 meters. So in order to map it, probably half of the day with a total station. Okay, so here is already our point cloud. We already have a very good feel for the 3D shape of the terrain. But now the first thing we need to do is we need to calculate the digital terrain model. So we will just quickly classify this point cloud, and we'll also see how the classification algorithm works. So here we have some settings for the classification algorithms. So these settings, they really work for 99% of all the cases. We just press next. Then algorithm is semi-automatic. We just select one point on the ground, and software, it goes like that through all the points, and it checks what's the height difference between these points. If they are on similar height, it will say, okay, this is terrain. Vegetation here, it's too high, to say, okay, from here to here, there's too big jump, this is not terrain. So it's very simple, but it gives one of the best possible results. So, the others, they use some more complicated stuff, but it gives you a lot of wrong information. So then in next step, we just do a little bit more of filtering. New surface is calculated, and then all the small bumps are excluded. So now we'll just press finish, and we will just use this delete other tool to just temporarily delete all the non-ground points. Okay, and out of these ground points, we will now create a new digital terrain model. Just press calculate, and already we have a digital terrain model. Now, in order to calculate volumes, we saw earlier, calculate contour lines. Just press calculate contour lines, select the equidistance. We can leave it at 1 meter or put it at lower, 0.5. Okay, it can be 2/3 of a meter, it doesn't matter. Continue. they are calculated almost instantly. On the other hand, if we want to calculate volumes, again, just select an area of interest, just like we showed you, press calculate volume. We will interpolate initial surface. If we had two surfaces, we could also choose the initial surface. The final surface will be the one that's in point cloud from current selection. And bam, we already have the volume, so around 600 cubic meters here. The bottom surface in this example, it gets interpolated, so out of the boundary. So here you see it goes a little bit up. So it's very important how this bottom surface is defined. This is most suitable when we have a pile of material on flat ground or excavation of a terrain from a flat area. For other examples, it's best, when we're calculating volumes, to do measurement 1 before anything is happening, and then measurement 2 afterwards, and we just compare the two surfaces between them. Okay. After we calculate the digital terrain model, we can also create volume calculation. I'll just turn this volume off, I mean orthophoto calculation. So here we now have the mesh. Out of this mesh, we will now create orthophoto. Press calculate. So again, orthophoto will calculate pretty rapidly, especially because we have a small area, but for bigger areas, it will take maybe 15-20 minutes to calculate the orthophoto. So that's if we have one like 500, 600 images, something like that. So in the first part, the images are reprojected onto the digital terrain model, and then they are also color corrected. So in order to get to the result, that will look like one picture. So, okay, now the process is also saving the result. Okay, I'll just turn off contour lines in order for them not to display over orthophoto. Okay, so this is now the traditional orthophoto. What's special about this one is that the roof is not in correct position, but the roof edge is very sharp. And also the detail here in these rocks, it's very sharp because it's calculated using traditional algorithm. So another option would be, I'll just close some projects here. Close this one and open a new window. Another option would be, instead of calculating digital terrain model, to create a digital surface model. So that's 3D model that has also buildings and trees included. Just have a quick look on the memory, what's happening with it, if there will be. Okay, perfect. We still have way more than enough. So in that case, digital surface model, it will look like this. So trees are like 3D trees. Also objects, they look like that. Okay, here we only have the roof of this object because it's on the edge, and we only had top-down images. Now, if we make orthophoto out of this one, I just have to recalculate it real quickly. So here, out of this one, it will also already tell us through orthophoto, calculate. Stop the autosave. Okay, so the difference between the two will be that the traditional orthophoto, it's sharper. On this one, if we check it out, so this is true orthophoto. If we look at the detail here, it's slightly less sharp if we compare it to this one. But on the other hand, this one has correctly positioned objects, while the other one, okay, so here you see roof at the exact position. Here it's slightly moved to the side. Okay, Now, at this point, I would like to move to second example. So here I have a nice example, and here we will now check what we can do about line work. So maybe now I will just close this window. Okay. So here I have an example of a house that we mapped. So this was a cadastral application. And for this one, you know, the area of interest is like 100 meters. Because it was that small, it allowed us to calculate, to record a lot of pictures. So we flew around the house a few times, but that really allowed us to get a very detailed 3D models. Here you can almost see here you can see what the people doing the survey were eating. If we check it in the 3D mesh, this will be even sharper. Okay, and you know, some people got here pasted onto the image. We were moving around, so that's why it looks like that. What's important is, so this was for, you know, this is a new building, and you know, we made a map out of this one. So what we did for this one is these points, the blue ones, we measured them with the total station. And you can see exactly where the total station, you know, when you measure with it, you hit just this point here. For example, for this part of the highest point of the roof, this is what we can measure with total station, but you know, the actual point should be up here if you drew it out of 3D. Now, so our 3D survey has an integrated CAT engine. So here you can choose, you can draw on point cloud, or you can draw on 3D models. So here, if I draw lines, I can select here, I want to have points on vertices. I want to snap on point cloud points. I'll just use this layer, for example. So now we're just snapping on point cloud points and just drawing the lines. So instead of, you know, mapping everything with total station, you can just draw the lines here. Another, maybe even better option than drawing on point cloud will be, we can turn off point cloud, go here. We can also draw on the mesh. So this is now the 3D mesh. Like that, we are drawing directly on the mesh. So anything we draw like this is automatically in 3D. So, you know, and here, you know, just for comparison, here is the outline of the building that I made out of this 3D data. And the blue and yellow points are the ones that we measured with the total station. So accuracy-wise, I would say that photogrammetry can even give you a better result than the traditional techniques. Now, one of the things that tends to be slightly hard is to get to these corners very accurately. So here 3D survey has an ace up its sleeve. So, and this technique is called point cloud X-raying. So let me show you how this works. Just select point cloud. So the problem will be, you know, in the point cloud to get these edges, or maybe this one will be even better example, because you see here the wall of this object is below the roof. So if you want to extract this out of point cloud, you know, you might struggle to get the correct point down here. But with X-raying, this will be simpler. We just select the resolution for our X-ray, press generate, and what we get is, you know, sort of like taking X-ray at your doctor. So then the walls of the buildings will come out looking through the roof like that. So what we can do then, we can paste that X-ray onto our digital terrain model. We can go to CAT, just turn the point cloud off, go to cat, and then you can just draw here. You can just draw where the building wall is, because the building's walls, they come out like this through the roofs or everything. And if we check here, we see that the accuracy is pretty good one. So, okay. So now this was a second example. I see we are some 10 minutes over our time limit, but I just like to make the third last example. So, okay, we now checked how we can do line work, how we can get the 3D data. I also want to do a very quick demonstration on the volume calculations. So I'll just open a new window of 3D survey, maybe close this one. Okay, here, let's just switch to this view. And let's also look at one construction site project. I have an interesting one here, construction. So now in this project, so what I want to show is 3D survey is not just a tool to create the 3D data, it's also a tool for analysis of the data. So here we don't have any images inside, we just have 2 point clouds imported into the software. So this was the situation in the beginning on this construction site. This was situation maybe half a month later. So we'll just quickly make 2 digital terrain models like that. So digital terrain model 1, digital terrain model 2, calculate. So, we could do it like before, just manually select where we are calculating volumes, but actually it goes like that. So the civil engineers, they will give us area of interest, they will draw these lines and they will say, okay, calculate what's happening inside of this excavation site and calculate what's happening on the pile. So this is now in 2D, that's why it comes out like that. If we want to see exactly where it is, we just go to ortho and top-down mode. Now, in order to calculate these volumes, like we showed earlier, just select calculate volume from DXF, select that DXF with boundaries, and we already have the volumes. So if the boundaries would have been on layers with name, we would also get the layers, but I'll just write here excavation. And the second one is the pile. Okay. We now have our volumes in 3D. We can already see them pretty well here in the volumes tab. So it shows here where the material was added to the site, where it was taken away. So here most of the material was excavated, just here a little bit was added. And here the situation was a lot more complicated. Now the second step will be to calculate some vertical cross sections, for the report. So this one, calculate profile. I'll just quickly make 2 of them. So here is the first one. It's already visible here in 3D and here in 2D view. Let's make another one. And we also have another one inside. So now all we have to do is generate report, measurements report. It's already set. Here I want to also add this to volumes, calculate. And that's it. Here's our report document. It's a Word file, so you can easily add in your company logo, and you get the first area where we calculated volume, second area, and where we have vertical cross sections and the cross sections themselves. Okay. Now, last but not least, I just want to open one. So very often the question about this kind of data is what will be the accuracy of this? So I have here a project from one of our customers who was wondering just that. What kind of accuracy can we get from this data? And first of all, she had to have a very good GPS. because she measured some 200 points in her area of interest, to check the accuracy of this data, and it came out very, very good. So we will see this later. Just wait for this to load, and in the meantime, I'll just close this one. Okay. So here is her point cloud. So what she did is she measured. So one of very good functions of 3D survey, you can do this trick. You use load cat, and then you just select a txt file. So in this txt file, we have some point name, x, y, z coordinates. Load this one in, import. So here now in this tab, we can then just check for each point. We can check the delta height, what the delta in height will be between this point measured with GPS and point from the point cloud. Let's make the text a little bigger. We will be snapping on points. Let's check this one. And we don't want 3D distance, we want delta height. So here we see around from 0 to okay, no, I just have to repeat this because now it's still showing that one. Now it will be showing delta height. So this one is actually around 2 to 3 centimeters. And we can just check for a lot of them. So most of them will be less than a centimeter. We have the difference of less than centimeter. So this one is 0, 0, 0, 1. Okay, let's leave it at 1 centimeter. Let's check this one. 1 centimeter, 2 centimeters. And we have 100 of such points. Okay, in the grass, the difference will be slightly bigger because with photogrammetry, we measure top of the grass. With GPS, we stick it in a little bit, so that will quickly add a centimeter or two. Other than that, we can easily check the accuracy. So for this data set, we had some 200 points. We measured the accuracy. So for here, it was on average, the offset was, I think, around 1.8 centimeter, something like that. So pretty good if you consider how much data we have in here. So, and it would be, kind of pointless to spend 2 days mapping this area with TotalStation if we can do it in half a day instead with the drone. So, okay, these were now some practical demonstrations. I'm sorry because we went slightly over our budget with time. So at this point, I would like to welcome you to visit our webpage. It's at www.3dsurvey.si. So here you can click to get a free trial for our software. You will also find some case studies. There will be an option to get some additional webinars, some tutorials, something like that. In the download sections of the webpage, you will also find some sample projects. Interesting part could be also the case studies. Maybe it can give you some additional ideas what can be done with this software. So here, for example, we have a project where instead of a drone, just a phone camera was used to map the insides of the building. And when you build a house, you then always search, when you build something new, you always search where you have the installations. If you make a map like this in the beginning, you will be always able to just measure where the installations are. Okay, just one example. Come here and find about more interesting case studies. Okay. At this point, I would like to also bring your attention to the poll. So we will do a short poll now. It will be asking you about this about this webinar, what kind of answers were given. And at this point, I would like to hand the word back to our colleague Quiam. We'll also have a few words for you now. Go ahead,
Right.
Quiam, please.
Thank you, guys. We just want to say thank you for the guys that joined us for this webinar. We really hope that you got a lot of value and have some new insights in drone mapping. If you have missed any questions, please feel free to send us an email or even message us on Facebook. Thank you very much, Vid, and the 3 Survey team for hosting this webinar and for sharing your expertise.